Thank you, everybody. It's a great opportunity to talk to you all, and there's a whole bunch of folks here. That's good. We're all going to be done. My name is Siva Venugopalan. I've been in this business for over 35 years, looking at NDT, corrosion, concrete structures, and that kind of thing. I have a double master's, geotechnical materials and corrosion, and I have my contact information there. So if you want to talk to me, you're welcome to give me a call. So we've been in business for quite a long time. As you can see here, we specialize in deterioration of concrete materials as it sits in different environments, reinforced concrete material. We understand what the current condition is, what the gaps you have. Thank you. What the gaps you have, trying to figure out what data we need so that we can define the actual remaining service life and how to address those over time to provide a cost-effective solution for the clients. These are a number of different areas that we work on, so I'm going to pass that since we are 3:20, move on. So let's talk about AASHTO spec. And what we're talking about service life, I want to give you a little bit of history of where we come from. In the 40s and 50s, when we're building a lot of those bridges, one of the things that AASHTO specified is a design life of about 50 years. And at that time, we thought it was a lot of time. And now we are here, 2025. Number of these structures not only are deteriorating and deteriorating at a high rate, but we don't have the money to replace all of these structures. So we're trying to extend the service life of these things. Marwa talked about it, how we're actually improving the process of predictive modeling to figure out how you can get closer to the actual service life, remaining service life, and how we can spend the money to extend the service life. And, I think why is it such a big deal that we're talking about it, right? Primarily, it affects people, It affects traffic, it affects the time, it affects the money that you spend. It's a safety factor, a lot of the structures. So right now, recently a bridge failed because of the weathering steel corrosion issue in Pennsylvania and my state. And NTSB has issued a report I read through cover to cover. The cause is corrosion. So, better structures are better for the environment. The longer we keep a structure, we're actually improving the environment as well because we're reducing the input into the thing. So what happened? Over time, AASHTO has gone from 50 years to 75-year service life. When we talk about design life, 75 years, what do they mean? You really have to understand how do they define this, right? Now we talk about here 365 or Life 365 or FIP 34, we talk about service life and not design life. There's a difference. How you look at it, how you understand it is critical. Now FIP 34 also talks about taking it to 120-year service life. People are trying to extend it beyond because I've worked on structures that already have been there for 85 years. We're trying to get another 50-year service life. So we are well past the 100 years that we're thinking of, that we're designing the new structures for. So we really have to get our hand around this whole process of how to predict service life and, whether it's existing structures or whether we're building new structures. And we also have to do it in such a way that we're reducing the overall cost because the builders are trying to build and they have to manage the overall cost, whether it's the owner or a builder, either one. And so we really need a clarification in terms of what do we mean when we say, I want the service life? Is it at the end of it, we throw it away, put a new one in? Is it the end of it? Oh, we really have to maintain this, or is somewhere in between? We really need to know how we're defining this. If we don't know that, we're just putting something out there which may not provide the intended purpose, right? So durable design consideration that you're looking at, not simply design. You really have to have a good interaction between the designer and the material specialist or service life specialist. There are a lot of different types of structure, or the elements that go into a structure could be all the different types. So you really want to know elements of that particular structure that you're dealing with. And you got to break that down into different parts, whether it's replaceable or non-replaceable, so you have an idea of what do I need to really focus on, what can I manage and maintain so the overall cost is minimal and your carbon loading is also minimal, right? Environmental loading is another thing you want to look at, right? A lot of the folks are thinking about these days de-icing splash zone, but there are a lot of other things. We just heard from this gentleman about AAR. That's a big issue. And a lot of the structures that I deal with, it's 30 years old, there's so much ASR issue that it's really going to be expensive to even repair and maintain that for another 70 years. And so the only solution could be at some point in time, tear it down, put a new one. And so what do we want as a service life? We really have to get clear in terms of what we want. If we don't know what we want, we don't know what we're doing, right? And so when you come to service life, the strategy for achieving that service life that's defined in the particular contract document is either you can do deemed to satisfy or the probabilistic model or a number of combination of these along with avoidance. When it comes to severe ASR, one thing you may want to think of is just not use the material. Well, is it even possible that you can use the material if that's the material that's available locally? The contract's not going to truck aggregates from hundreds of miles away just to build a bridge. It's really not going to happen. So how do you then minimize that? It's really important to strategize how we're going to attack those things. What type of materials that we're going to use? What is the resistance of those materials to the environment that we're dealing with? And then other issues, jointless detail, things like that you can do. These are a whole list of things, not complete, but most of it is addressed. These are the things you have to think through when you're talking about durability design for a 100-year service life. And you also have to think about how are we going to maintain that structure throughout that service life and beyond. And how you define the service life. In FIP 34, it defines the service life as initiation of corrosion at the end of service life with a certain reliability, right? That's really what we're looking for. At the end of service life, it's not that you tear it down. At the end of service life, you start spending a little bit more money managing the structure beyond the structured management that occurs within the first 100 years of its service life. So the other thing is you really want to look at the project requirements. A lot of the folks, they know the service life, they know all the documents, but really you need to marry what you know from your activities here to what the structure actually is defined structure requires as a minimum. They have certain minimum requirements. You want to know and understand what the minimum requirements for that particular structure is. You want to know what the codes are applicable for that particular structure and the limitations of the project site. Like, for example, the aggregate I'm talking about, right? So if you have certain limitations, you want to keep that in mind before you start that your service life process. And delineation of different parts of the structure. You want to know, hey, what are the things that I can never replace? I have to have 100-year service life. What are the other ones that I could probably replace that I can go with different approach towards addressing those issues? Work with the team, design build team, from early on in the process. You want to know what the structure is, what they're thinking, what are the different options they're thinking. You want to have that engagement, conversation with them early on until you understand, you start thinking through all of those before you get to actual design. You want to get all those specifications put in place. Here's the cover, here's the type of steel that's available, here's the type of cements available, here's the source of cements available, here's the aggregate that's available, here's the cost. And so ranking the cost and availability, all of that need to be in place for you to start the process of design. So these are really important. Once you do that, you then look at the project minimum requirements and identify if the client has specified anything specific in terms of what the minimum service level requirements are. Once you have those, you list those in, and then you look at what the exposure condition for each of those elements are. You identify those. And then you have the full list of all the materials you have. and you'll be able to start your process of, okay, how do I do this? Now, I'm not going to go through all of the different deterioration parameters that I talked about. I'm going to focus on the chloride diffusion model using the FIP 34. There are a lot of different models out there. You got Life 365, you got FIP 34, you got the Stadium model, you got a couple other models, diffusion models. So I'm going to focus on this one, otherwise we'll be here until 5 o'clock. So what this diffusion parameter basically says that you have a certain amount of time for the chlorides to accumulate at the reinforcing steel, whatever the depth it is. And then once there is sufficient chloride accumulation occurs, assuming your pH is high pH concrete, then the initiation turns into propagation. Once you have sufficient, what happens? Then the passive film is broken down by the amount of chlorides that's in there, initiates the corrosion process, which results in concrete damage over time. And Marwa talked about it, right? When you take that chloride from one point to the other, there's an increase of deterioration. That's kind of what it goes on. So we are focused on this particular area here. We're focusing on how do you get this service life to go where you want it to go, which is 100 years. Now, what happens typically here, when you get the higher chloride exposure for a given cover and a given type of steel, you really have this initiation point defined. So you really need to know what your parameters are. And for a black steel with a certain de-icing exposure, you may not get 100-year service life if you don't really work through the process of figuring out what are the other parameters, right? Probabilistic model allows you to look at various parameters: is cover, type of steel, cementitious content, water cement ratio, exposure type. You can vary all of this to try to figure out which combination is going to give you the service life you want and also reduces the overall cost. And so the model code, I'm going to skip through this. It focuses on durability and degradation management as well in terms of over the intended service life. You're not just talking about producing something today. You're talking about not only producing something today, but it's going to last through that lifetime, 100 years, right? And to do that, the probabilistic model requires a lot of different input. The primary input that it requires is the diffusion property for that particular mix that you're thinking of, which is called the CMC, right? It goes directly into the model. And these are a number of variables that go into the model. I'm not going to go through each one of them, but we look at a few of these. When you put that together for the different elements and the required service life and where your surface chloride levels are and type of concrete you're going to use, you come up with the maximum allowable chloride migration coefficient. Once you have that parameter, you then actually put that particular mixed concrete and measure your CMC in the lab. Now, if that CMC in the lab that you're going to get is less than what the maximum allowable is, then you're okay. If your CMC measured is higher, then you're not going to get the service life you want, right? So that's really important for you to figure out. And if you look at this, these are the various different parameters. It's not including all of it, most of it. So increasing service life occurs when you have your CMC number that are lower, right? And same way with your surface chlorides going down, your service lives get better, given all the other parameters being the same. So these are the different levers that are available. We can push it one way or the other. It will affect your service life. So there are some things that you cannot avoid. Background chloride, it is going to be what it's going to be because of the aggregate that you use, cement that you use, whatever you use. So you have to know that. If you don't know that, that might affect your service life. And the critical chloride threshold is defined by whatever material you're going to use, type of steel you're going to use, right? Those will not be changing. And the surface chloride, you have to figure out what the surface chloride is going to be. A lot of the states have sufficient data that you can actually predict what the surface law is going to be in that particular area you're dealing with. So you want to use the actual that you get a lot better than simply using the default parameters if you can. So when you do that, let's assume, assuming all other factors being the same, the quality of the concrete identifies what your service life is going to be. For example, for a CMC of 0.35, which is reasonably good concrete, you get a service life of 120 years, let's say, for all other parameters being same. But if the same CMC number goes over to 0.55, which would be very high, water cement ratio and all that stuff, your service life is significantly down. So this is one thing that you have to keep in mind, that CMC is really important, it's really critical. You want to measure that, and you want to make sure that your predictive model says that if CMC is this, and your measured CMC should be higher than the predictive model. So you know that you're going to be fine there, right? And when you think about the cover, typical design cover for the deck is about 2.5 inches. Average, right, design cover is about 2.5 inches. Now, you cannot increase to 3, 3.5, 4, 5 inches, because there is a law of diminishing return, particularly when it comes to cover. So you don't want to have cracks. So typical cover is defined as 2.5 inches, and if you use that and your model indicates 85 years of service life, and if that cover should reduce, what do you mean by reduce? She talked about the standard deviation. If you use an average defined cover of 2.5, when you build the structure, it's not going to be 2.5 everywhere. A couple other presenters talked about it too. If you have a really tight control over your construction, your standard deviation, based on all the work we have done, 0.25 is normal, reasonable. If you have a 0.25 standard deviation, you get very good chance your lower end of the cover is going to be 2.25, 5% of the structure. So that value, the service life value, goes down from 85 to 45, almost half. So you really, really need to pay attention to your cover. And if you pay attention to your actual controls during the placement of the concrete, the rebar location, things like that. If you go to 2, which is standard deviation of half, your life goes really way down. And so I've seen some structures where you have a standard deviation of half, not 0.25. 0.25 is better, which I've seen, and you could do even better, 0.2, 0.15. But there's never going to be 2.5 everywhere. It's a given. So it's really important to know what your cover and what the variations are, and that would make a huge difference. Now, we talked about this 2.5, and if you take it to 2, you cannot even put a structure in there, get a service life, right? Look at the chloride loading, right? That's another thing, because the structure is exposed to the environment. If it is mid-Atlantic, if it is northeast, or if it is Midwest, where she lives in Chicago, they put a ton of salt, right? And if you take the same structure, you put it in the Mid-Atlantic, like North Carolina, Virginia, you may get an 85-year service life. You take the same structure, put it over there, you're not going to get an 85-year service life. It's important. So how your chloride cover affects it, how your chloride loading affects it, you want to understand. We all know it affects, but we want to know how is it going to affect my structure in the place that I'm living in, and that you want to design that. And so there are a number of other things you have to think about, and of course, this AAR issue is still worked out. The gentleman talked about it, and there's, we probably don't have this standard anymore. We have the new Canadian standard that we're working with, but this whole thing needs to be really paid attention to, because if the AAR is not addressed, it'll come back to bite you. So this is one of the videos. This is a project that we worked on. We actually did the service level modeling. used all of this information plus the surface chloride that we got from all the 50 different bridges. We put that in, we put that together, and that's we received an award for the project. So that closes out. If you have any questions.